we could solve for our total first, we could do that. And that's fine and dandy. But I have two values here in this load. So I got 1500 ohms and I have 2 amps. Now, I can find the voltage in this branch, and in a parallel circuit, finding voltage is critical because why? Because whatever the voltage is on this branch, it's the same throughout the circuit. So E equals I times 3, correct?
Yes.
So 2 times 1500 is 3,000. So my voltage here is going to be 3,000
3,000?
3,000.
volts.
3,000 more?
Over here, I've got
3,000.
3,000 volts.
3,000 volts.
Okay. So that's good. That's cool. We like that. That's awesome. Now what we have is we've got to find R total. Now we have E total. We have the current of one branch. So the only way we're going to find I total is what? We're going to go in here and we're going to have to. But what I can do, I can find R total, but I say to you, I really don't want to use this formula, so I'm going to take a different approach to solving this particular problem. Well, what would that be? Well, okay, if I know that this is 3,000 volts, and this is 3,000, and this is 3,000, right? Right. So what I have now, I can figure the current in each branch. So I'm going to figure the current in branch number 4. So this is going to say 3,000. Why didn't that work? 3, there it goes. 3,000 divided by 750 equals 4. So this one's got 4 amps. Cool. We got 2 amps here.
4 amps.
Given. I'm going to come over here. So I've got 3 divided by 80. That equals 37.5, right? So this is going to be 37.5 amps, right? Right. Now if I got this one over here, I've got 3,000 times, times,
Divide.
1, 2, 3,
By
divided by
40.
How much?
75.
75 amps.
75.
So, if I take 75 plus 2 is 77, plus 4 is 81. So if I take 81 plus 37.5, I total is 118.5 amps, right?
120?
Because in a parallel circuit, I total equals I1 plus I2 plus I3 plus I4. So I add them all together and that's what I come up with. Is everybody cool with that?
Yeah.
So now I have this. Right now I can do what? I can find R total. I don't have to go through that reciprocal formula. What is R total? E divided by I. So I take 3,000 divided by 118.5 equals 225.316. Now, let's do the eyeball proof. The eyeball proof, before we ever started, I have 4 loads in parallel. The total resistance is going to have to be less than the smallest load in the parallel bank. That's 40. 25.316 is below 40. My eyeball proof works. So I'm going to say, oh, okay, now I can double proof it by going and using the what? I can use this formula down here, do all the math and walk myself through that, right? I don't want to do that. I'm a lazy mother. So I'm going to come in here. Now let's find P total. P total is going to be 3,000, right? Times 118.5 equals 355,500.
Come on, 3,000.
Everybody cool with that? Okay. So I could say, or I could write that out.
What?
355.5 kilowatts, right? Same difference. Okay, so there we go, and I can come back here now and I can work out all my individual values.
Okay.
In this particular case, I can take 3,000 times 75. That's 225,000.
105.
I can take 3,000 times 37.5, that equals 112,500. I can take, this is gonna be 6,000, or 6 kW. And this is gonna be 12,000, or 12 kW. Well, that's
Cowway.
18. Three 55.5. Comes out exactly, right?
Remember when you
Yeah.
Okay. So, what did I do here? Yes, we took a different path.
When you put the kilowatts, you use the 0.1.
We took a different path towards solving this. I avoided the big reciprocal formula, but I did a double proof. And the double proof I did was, I came back here, I figured my power, and then I came back and I did all my individual power, added them up. Since that equaled my what? My P total, I know that everything in this is dead nuts on the money. Is everybody cool with that?
Cool.
So the currents added up to be fine, the power added up to be fine, and what? It all balances out with my resistance total. So this is another way to solve this. You don't necessarily have to go all the time to your what? To your reciprocal formula. Does that make sense to everybody? Okay, now, what's gonna happen here is, again, we can do this for as many branches as we want. Notice here, and this is crucial now, let's take a look at the presentation we did at the beginning of class today and wrap that back over here onto this problem. This in fact could be a very real world problem, couldn't it? These represent loads, not resistors, right? And if I did this, what am I seeing? Let's analyze this now, because again, I want you to put 2 and 2 together, so when we're working with live circuits or real circuits, you've got it down. So the wiring here, correct, is gonna have to be able to be sized to be able to carry 118.5 amps. Everybody cool with that?
Yeah.
Now, you're gonna say, and you can say, well, yeah, okay, yeah, but this only pulls 75 amps. So I'm gonna put 75 amp wire here, then I'll put, 37.5 amp. It doesn't work because these wires have to carry all the current. It's only got the one path coming around, I'm leaving on one path from the power supply, I'm returning on one path. So therefore, it's gotta carry the current for all loads in the circuit. So this is again what we're doing. Now, if I only have one load up here, right, then the wire only has to be big enough, carry 75 amps. But because I'm adding all these other loads on, I'm adding current to the size of my wire, and that's what we gotta do. We've gotta size the wire for 118.5 amps. Everybody cool with that? Now, the other thing that's real interesting about this, and this is, again, I wanna drive this in everybody's head, we keep talking to you about the resistance being inversely proportional in a parallel circuit. Well, we can prove that just by looking at this. We don't have to do any math. We can prove it by looking at this, because here's the deal. This is the smallest resistance in the circuit, right? Correct? And if this is gonna be the currents that we know are drawn by the individual loads, this is gonna be the power that each one of these puts out, right? Now, if you're looking at this and you're saying, okay, so if I have a 40 and an 80, right, and I'm getting 225 plus 112 power performed in this, if I add another branch, did my power go down or up? It went up. Well, the only way for that to go up is for the resistance to go down, because if resistance stays high, you don't get the current flow, you aren't gonna get the power. Does that make sense? You know, we're begatting again. One thing begats another, so this is how we draw the comparison and the parallel in these circuits, and this is what guys don't get when they go out into the field, right? They keep wanting to shortchange this. Now, you don't know this, I'll throw this out here, because we're gonna be doing this probably about 2 weeks, but, these wires have their own special sizing calculations, right? They have their own special rules, their own special tables, their own special code requirements that we have to comply with in order to what? You see any calculation on this problem for the resistance of the wires? No, because it is assumed that we have sized the wires correctly to avoid voltage drop, right? We are assuming. Now, I'm beating this as a dead horse. I keep coming back to this theme. This is about 5th or 6th time I've done this, because that's what we have to do. We have to what? We've got to get the correct power supply. We've got to get the correct wire size, and then we have an additional size. 118.5 is the starting point. Then we have like 5 other factors that we have to weigh in sizing the wires, right? To get the wires to the right size. And then once I do that, bingo, I got a circuit. Does that make sense, everybody? Now let me ask you this question.